Welcome. We are now ready to begin constructing confidence intervals for an unknown population mean, and we'll be looking at the case where the population standard deviation, sigma, is provided. All right, so first I just want to draw your attention to the image here. So in the previous chapter, we learned the central limit theorem, which said that if we had a population with mean mu, and we took samples from that population and we did so repeatedly, that the graph of those sample means would follow a bell-shaped distribution or a normal distribution, assuming certain conditions are met. And we'll go back to discussing those conditions a bit later. But essentially here, if our sampling distribution is normally distributed, the change is that mu in this chapter is unknown to us. So if we're not collecting data from our entire population, though we know that the population mean would be at the center of the graph, we don't know what that population mean is. So the purpose of this chapter is to use a sample mean to approximate it. And we do know that if we take a sample from a population with mean mu, that most of the time the sample mean should be close to that population mean. Now, it's not always going to be close. Sometimes you might get a sample mean far to the left or far to the right because samples are never perfect pictures of your population. But we do know that most of the time we would get values towards the center of the distribution. Now, in this picture, it says 95% for that area because this area with our confidence intervals will represent our confidence level. And we'll need to move forward and learn what some of the other symbols that are showing up here mean. So our first step in learning to construct the confidence interval estimate for the unknown population mean will be first to deal with z-scores. So before I get to the z-score here, let me introduce our lowercase Greek alpha. So first letter of the Greek alphabet is a lowercase. Well, there's upper and lowercase, but our alpha here that we'll be using is lowercase. And I know it looks kind of like the letter A, but it is not. It is alpha Greek, and I'll draw it for you in a moment. But alpha is going to be the complement of our desired confidence. So alpha will be 1 minus the confidence level. So we're going to be looking for, in this case, a z-score called a critical value that basically creates this picture. But instead of using X bar, we'll start with just z-scores, and then we'll work our way up to applications. So our first step is to find this thing called the critical value. So let me just slide up here. Okay. So number 1 says find the critical value. It will be a z-score, and the subscript on it is going to be alpha divided by 2. We'll figure out why in a moment. And we're going to start with, what if we're doing a 95% confidence interval estimate? All right, so on my picture here, so I'm going to just label my axis. So we're going to be doing z-scores here. So in a normal distribution, standard normal, there's 0 in the center. And 95% confidence means I want this middle area to be 95%, but we'll go ahead and do it in decimal, 0.95. All right, so what's left over in the tails, what I've shaded here, what's left over in the tails is what we call alpha. So the area in those two tails together would be the complement of my confidence level. So alpha will be 1 minus your confidence level. I'll just write CL, confidence level. So if we have 1 as the area of the whole graph, and we took away the middle part, 0.95, that would leave me an area of 0.05. So these two together would have to be 0.05. Now I'd like to know how much area is in each tail separately, and the graph is symmetric, so the area in just one tail, we just take our alpha that we got, divide that by 2, so 0.05, divide that by 2 is 0.025. Okay, so let me label some things here then. The area in the left tail, and you'll see as I'm drawing my alphas here, they end up, I don't know, sort of looking like a fish, but I sort of exaggerate it so you know it's not the letter A. So that's how you'll see me draw my alphas. So alpha divided by 2 came out to be 0.025. And then that area in the right tail would also be alpha over 2, 0.025. All right, so the z-score that we're looking for will be the positive z-score that makes this picture happen. So that z-score, so z is called z alpha over 2. So subscript alpha over 2. So it's going to be the z-score where the subscript tells you the area to its right. So I'm just going to label this. This is the area to the right. So z alpha over 2 is generally how we would write it for any for any confidence level. For this specific example, our alpha over 2 was 0.025. So the z subscript 0.025 is the z-score that puts the area 0.025 to its right. Okay, so next, I want to find that z-score. So we know when we're trying to find a z-score, we can use inverse norm on our calculator, as long as we remember when you inverse norm, you don't inverse norm what's to its right, you inverse norm what's to its left. So we need to know this area to the left of that unknown z-score. So if the area to its right is alpha over 2, then the rule of complements would say the area to its left is 1 minus that value that we got for alpha over 2. So 1 minus 0.025 is 0.975. So on my graph over there, 0.975. Okay, so we always want to remember that you're always going to inverse norm the area to your left. So here is our summary. So if you want to find z alpha over 2, in our case, it's z alpha over 2 is 0.025. You will be inverse norming the complement of 0.025, 0.975. That's your 1 minus alpha over 2 value. Okay, and then on our calculators, we go to our distributions, inverse norm, 0.975. And we will either be rounding to 2 or 3 places. So we'll see both. And generally, I would let you know. So for now, let's just do 2. So 1.96. Okay, so on my graph over here, we're almost getting to 2, but that answer is 1.96. So that z-score, called the critical value, z alpha over 2, generally speaking, is always this positive one. So the other z-score, because of symmetry, would be the negation of that number. So that would be negative z alpha over 2. So right now we're not interested in the negative. We're just going to be looking for our critical value. Okay, so new notation to get used to. So let's just step through another one here. And instead of a 95% confidence interval, I'll drop it to 80%. So I'm going to make this area smaller, which you'll see on the next picture. Okay, so find Z alpha over 2 for an 80% confidence interval. So the center area here is now 0.80, 80%. Okay, so alpha. Alpha is 1 minus the confidence level. So 1 minus 0.80, 0.20. So if 80% is in the middle, that would be 20% is left over in the tails. And to get each one separately, you take your alpha value and divide it by 2. So just take 0.20 divided by 2, and that is 0.1. I just like putting the 0, so it looks like 10%. So this area on the left, this is the left tail has area alpha over 2, and the right tail has area alpha over 2. The z-score that we're looking for is z alpha over 2. So just generally it's called z alpha over 2. So it's the z-score that puts alpha over 2 to the right of it. So for our specific example, that would be z subscript 0.10, because that area is the area to the right of it. Okay, but we don't want to inverse norm the area to the right of it. We want to inverse norm the area to the left of it. So if alpha over 2 is to the right of it, 1 minus the alpha over 2 value is to the left of it. So for that z-score, 10% is to the right of it, so 90% is to the left of it. And you can also see this 0.90 showing up if you just add those two numbers together, 0.90. Okay, so for our example, z alpha over 2. So z alpha over 2, 0.10 as a subscript. We inverse norm the 1 minus alpha over 2 value. So before I go to the calculator, it's important to see here that you're never using the 80% directly here in the final calculation. So there are steps to go through to know what you're going to inverse norm. And then once you get through those steps, you're back to your distributions, inverse norm, 0.9. And I'll round to 2 places again. So that answer is coming out to be 1.28. So I'll put that on my graph as well. So that positive z-score there to create that picture is 1.28. So that is called the critical value. And we're just interested in that positive one here as we will be moving forward. So that is 80% confident. So we're going to do one more. We're going to look for z alpha over 2 for a 90% confidence interval. And I'm going to call this one a rounding discrepancy case, which we'll talk about here as we step through it. Oops, sorry. Okay. All right, so let me write down all the notation here as well. So let's start with our alpha. So alpha is 1 minus your confidence level. So 0.90 for 90%. So 1 minus that will be 0.10. And then alpha divided by 2 tells you the area in each tail individually. That will be 0.05. So let me put that on my picture. So 90%, 0.90 is going to be the middle area. And then I'm just going to concentrate on the right now since I want the positive z-score. So alpha over 2 is 0.05. That's the area to the right of the z-score we're trying to find. So z alpha over 2. So z subscript 0.05 for this example. Okay. Now I need the area left of it. So I'm just going to come back up here. So the area to the left of it is 1 minus the area to the right of it. So 1 minus your 0.05 will give us 0.95. All right, I'll put it on the picture as well. So we're going to inverse norm that area to the left of it to find that z-score. Okay, so z, alpha over 2, or in our case, specifically z subscript 0.05, we would inverse norm 0.95. All right, so it's always sort of the 3-step process here. So you can figure out what you're supposed to inverse norm. Okay, I'm going to clear my screen here and inverse norm this one so you can see why I call it a rounding discrepancy. So I'm going to inverse norm 0.95. And I know I wrote 2 decimal places for the previous ones, but I'm going to write 3 here. So 3 decimal places here would be 1.645. So if we were rounding to 3 places, that is the answer. So the issue with rounding comes when we're talking about rounding to 2 decimal places. So let me explain here. I'm going to do sort of 2 scenarios. So let me just ignore the calculator for a second. So let's say that we were not using technology and we were trying to find this z-score. So what we would do is look it up in a table. So there would be a table of values that we could reference. And the table would say, for example, the answer is 1.645. And that's that. So that is the correct answer. But what if we were asked to round to 2 decimal places? So if the only thing I had to look at was that number, no calculator, I would see this number. And if somebody said round to 2 places, that would be 1.65. And that will be the value that would be used in our textbook. So that's been traditionally used when you were rounding to 2 places for this particular z-score. So the rounding discrepancy comes because since we have technology, if you look at my screen here, if I were looking at that number and somebody said round it to 2 places, it would be 1.6. Well, now it would be 1.64. So my other option over here, shouldn't it be 1.64? So in the end, this isn't a major deal. It's just that it gets confusing for people learning statistics here for the first time, because how do you know which one to use? So some books will use 1.64, some will use 1.65. So essentially, we just sort of follow our book's guideline. So we'll be using 1.65. And we'll just understand that because we have technology, we would know that that is 1.64. But to follow the world before technology, when we would look it up in a table, table values would round it to 1.65. So I just put a box around this one. So we just basically have to remember that when we see this value on our calculator, rather than writing 1.64, we will go with 1.65. So that's why I call it a rounding discrepancy. and it doesn't come up anywhere else. The previous ones that we did were no issue. It only comes up with this very specific Z-score. So I'll remind you of that as the semester progresses. But there you have it. So 3 examples there of how to find the critical value, and then we'll learn what that critical value is used for coming up.